So I would just request everybody to please mute their mics so that we can start. We will wait for just 2 minutes more and then we'll start our webinar.
Okay, sir. सर आपके सामने रखोगे आप है एक्चुअली है ना वीडियो स्टार्ट नहीं किया है स्टार्ट हेडफोन सर नेटवर्क खूप कमी है ठीक है सर आपको पेमेंट करेंगे ना अपने को अभी
लैंड कनेक्शन कर दो ना
लैंड से जो यार टू ले लिए
यार ये वाला लैंड जो लगा हुआ है
ये बंद कर रखना चाहिए वीडियो सिस्टर आप इसमें तो जब पैसे नहीं करोगे यार अभी पेमेंट करेगा वो हाँ उसमें करेगा उन्होंने बात करते करते बता रहे यार आप लोग थोड़ा सा रुको है ना
Hello. Good morning, Dr. Florian.
Yeah, good morning. I'm very sorry I had a technical glitch and caused some delay, but now I think it's working fine.
Yes, so we'll start the webinar now. So as discussed by Mr. Ayush, we request all to mute themselves, and we'll take the Q&A session at the end of the lecture. Dr. Florian, you can just unmute yourself. I have just muted all.
Okay, good.
Yeah,
I will also switch off my camera because my face is not that important. The presentations is more important, and it should save a little bit of bandwidth.
Sure.
So good.
Yeah. So good morning all. Today we have Dr. Florian Kren with us. He has graduated in civil engineering from TU Graz and pursued PhD in mining engineering from University of Leuven. After completing his PhD, he has been associated with GeoConsult, where he worked on different aspects of heavy construction engineering with emphasis on tunnel design in all phases of a project. Since 2009, he is Managing Director of GeoConsult India Private Limited. Under his leadership, GeoConsult has provided consultancy services for oil storage caverns, road, rail, and metro tunnels. GeoConsult India, along with Dr. Crane, has always been a very strong supporter of TIYM in all of its activities since its inception. For this, we are very grateful. We welcome you to our webinar platform, Dr. Crane. Over to you.
Thank you so much for this very kind introduction. Yeah, the young members was always something we supported very much because at the end of the day, we all want you to stay in the tunneling business and to grow there. So a little bit of support in the beginning is always required. So, and I'm also very grateful for having the opportunity to give a little bit of time for the young members for this webinar. And I hope that everyone can take a little bit from this webinar and that few questions will come up. And to be very honest, it's a very broad topic and everyone has to dig a bit deeper into that because in say 1.5 hours, 1 hour, you can only scratch the surface.
Yes, Doctor.
So,
sure.
The question is now, is my presentation visible?
Yes, your presentation is visible.
Perfect. Thank you. Then I will start. The topic is TBM tunneling. I'll start with a brief overview And then basically, since we are a design consultant, I'll go into the direction of associated design tasks, mainly in urban area, because certain things are not required, say in areas where you have higher overburden, then the tasks may change. So this is not considered here. So a short overview, introduction, short light of metro tunneling with the TBM, planning and design, and I put in here impressions that I've cut a bit, and useful literature or references I will also give, because there is a massive amount of freely available references to study, to see what all is required for the TBM tunneling. So let's get into the topic. Tunnel boring machines, they are around now since some time. When you look at these two pictures on the left-hand side, you see the fully built up hard rock TBM. And if you look a bit more in detail, you can see here the cutter head, the shield. But what is interesting is this here, because here we have grippers with some provisions for installing support, and then the whole back end trailer is also already prepared. So this machine is ready to go for some long tunnel. I would guess this was a picture from the Swiss Alps, so it's about a 10-meter TBM. The discs can also be seen nicely. And here on the right, we have something that looks completely different, but we also call it TBM. And that is very clearly visible, a soft ground TBM. I don't have any disc cutters. And my whole face support is happening here, and the shield is going through and through. If you compare it with that shield is going through, and that machine will most probably be for some of the metro tunneling sites all over the world. Now, there is a whole range of TBMs, as we would call it. This shortcut DAUB, that means the German Association for Underground Works. They are part of the ITA, and they have already brought out some very comprehensive guideline also on the choice of machines. And this is how they subdivide the different types of tunneling machines. And I think this is generally accepted nowadays that this subdivision exists. So we start on the top with tunnel boring machines. Fine. The first thing is the open tunnel boring machines, so-called gripper TBM, which would be used usually in hard rock. Then at the end, or at the bottom here, we have the tunnel boring machines with a shield, or single shield machines, as they are called, for hard rock. So they are open machines. And then there is one thing which is very specific. This is so-called extension tunnel boring machines. This is when you have one smaller diameter and you extend it. For that, there is also specific machines. This I will not touch at all here because it's very specific and seldom used. So then still under the umbrella of what you would call hard rock machines is the so-called double shield machines, which I will show a bit more in detail. It's, so to say, a mix of a single shield machine and an open gripper TBM, marrying these two principles. And then going further down to the shield machines, Shield machines can have full face excavation. This is basically the types we use in urban tunneling. Without support, with a mechanical support with compressed air. Now it becomes interesting. Slurry support, that's the hydro shields. Earth pressure support. And without any support with a screw conveyor, this is basically running an EPB machine in so-called open mode. And then shield machines with part face excavation. This is that you have a shield, but you don't have a normal cutter head. This I will also not cover in this presentation. It's too specific and they are not used. So let's go further. Now this is what is called the classic open gripper TBM, which is used in hard rock tunneling. And the specific things is that the machine itself has grippers which fix the machine so that the machine can drill. So basically, the grippers are the abutment. They are pressed against the wall, the already excavated wall. And then the jacks are pushing the machine forwards. And the cutter head is, so to say, going through the rock. And there is an overhead protection shield and an area here where rock bolts can be installed as a primary support. So it can be easily seen this machine has no segmental lining. It can have a segmental lining, but it's not necessary. And the machine is pushing itself forward. So when these grippers are being retracted, these small feet, so to say, stabilize the machine. The grippers are advanced, the whole thing advances, and the grippers again push against the wall. So this machine requires, because of that mode of working, very good rock. Because if the grippers cannot be fixed against the wall, because the rock is too weak, then the whole machine will never come to performance. Now this is the next type, already used in hard rock tunneling, so-called single shield machine. And here we have segmental lining, and the machine is getting, so to say, its abutment for the driving from the segmental lining. So when this machine is used, a segmental lining is must. I have to have it because it is integrated in my whole working, like in all the other machines. So these machines are usually relatively short, strong. They can go through rock, mainly for hard rock. What is definitely the difference between all the machines which are used for metro tunneling is that I have no phase stabilization. Now coming to the next type, which is the so-called double shield machine. This type of machine is, so to say, a mix between the classic single shield and an open TBM, because this machine is having two shields, so, and also a set of grippers. So this machine can work using the grippers against the wall. Then the grippers are fixed, the shield is pushed from the grippers forwards, and segment installation can be done in the back. But the segments are not necessarily used for the checking or for pushing the machine forward. For that, we have the grippers. And if the rock is not favorable, so the grippers would not work, the machine can push.
Doctor. Actually, your screen is not being shared. I think.
What is happening? Oh, okay. Yeah, there was something. Okay, I'm sharing it again. No problem. I think now it's here again.
Yes, now it's visible.
Sorry, when did that happen?
It does
Right now?
just happen. Yeah.
It just happened. Okay, sorry. Okay. Then very brief. Here is the grippers in the double shield. Here is the checks, which can be used with the grippers for drilling. And here is another set of checks, which can be, while the grippers are fixed, be retracted. So segment building can go in one go during the drilling when the grippers are used. And if the condition of the ground is not good, one can use, so to say, also the line to push forward. The only shortcoming of that machine is that this shield is relatively long. It's basically 2 shields. So if I have ground which is having some time dependent behavior, I need to have some measures that the convergence will not catch my shield, so to say, especially the rear shield. Usually these shields are then a bit conical and the diameter reduces towards the end. Next thing is what is already used in metro tunneling in India. That's slurry shield, Herrenknecht, where I took the pictures because they are the best, is having these machines and they call them mix shield. So here we have something that is different to all the other shields and machines shown before, because here we have some pressure, some phase stabilizing measures integrated. And when you look at this, there is a slurry which is basically pumped into the cutter head and which stabilizes my face, which is very crucial when I'm doing soft ground tunneling with low overburden. The peculiarity of this machine is basically that also whatever is being excavated will be transported through pipes. So here is a small crusher usually inside, and whatever excavated muck is there, it will be transported, pumped out with the slurry, and fresh slurry will come in. So the green line is where the muck goes out, the blue lines is where the new slurry comes in. I mean, this machine requires a full separation plant, so there must be space and energy for that. On the other hand, if I have ground conditions, like for example in Bangalore, where I have quite hard rock, then this slurry has a big advantage that it cools the cutter head. So there is always a liquid coming in, which is cooling the cutter head and reduces, therefore, the wear and tear a bit. And the other very popular machine, and I think it's most of the TBMs used in metal tunneling in India are basically earth pressure balance shields. So for this one, a bit more details. Again, the cutting wheel is there, and behind this cutting wheel is the excavation chamber. And in this chamber, whatever is marked out, so usually it is soft ground, sand, silt, is being conditioned and is used to exert pressure against the ground. So that means I have this cake inside here, which is, so to say, conditioned with foams and other chemicals, which forms a paste which is holding against the ground, which may want to push in, including water pressure. And then this material is being mucked out with a screw conveyor, so to say, like this, and then dropped onto a conveyor belt, and then the conveyor belt can run through, or there is some mucking cars inside the tunnel, can be rail, can be on normal tires and the muck comes out. Now, one more detail here. You see here is an airlock, because when maintenance is done in the hydro shield and also in this one, the chamber is pressurized so that no water comes in. And therefore you need an airlock. In some places in this bulkhead, there is also an air bubble on top, which helps to basically stabilize the pressure and not to have any pressure peaks. So thrust cylinders, like in all TBMs, which rely on the lining as the abutment for driving, you have them here. The rector is there. Here is the tail skin, also with these brushes, which are there to keep the water out of the shield, and the backfilling pipes for the grouting, because there is a gap between our segment ring and the cutter head, and that has to be filled very quickly so that we don't get too much settlement. And for those who want to go into more details, the HK website is having interactive diagrams where you can click onto each and every part of the machine and get a detailed description what it is for. Now, I think the most important thing when we discuss about earth pressure balanced and slurry shields, because both are used in urban tunneling extensively, is really how they work. I gave already a short explanation. I mean, this is, so to say, a bit more in detail. We have the slurry coming in, the slurry fills the chamber. The slurry also outside creates a cake so that the pressure is maintained, which is especially important when you have a bit gravelly ground with a bit higher permeability. And then the material is marked out. And here is also standard in the slurry machines is this air bubble, which is basically like a damper if there is any pressure fluctuations. In the earth pressure balance shield, it is shown as shown here. We have this green area where, so to say, the whole muck is being conditioned and kept, and whatever is, so to say, to be transported out will go through the screw conveyor. Now, one thing is very important when we look at this screw conveyor. The material must be conditioned so that no water can gush through. If water goes through this muck, which is in the screw conveyor in closed mode, then we have a problem. Then they must, either we have to put in more foam or other conditioners, or worst case, there is a sort of a emergency closure mechanism. I think can be seen here, where the screw conveyor can be completely blocked. It's like a lock, which is being closed when, so to say, the conditioned soil in the screw conveyor cannot hold back the water. Because otherwise we have instability at the face, because the water flow cannot be stopped by the screw conveyor alone. There must be always some material, conditioned material, this muck paste, to keep the water out. On the other hand, as mentioned earlier, if I don't have water and I can go in open mode, then this is something I can do with the EPB, because if I have stable ground rock in open mode and the rock is not too abrasive, I can muck it out with the screw conveyor also. Something what I cannot do with a slurry shield that is always closed. So this is whatever I put in words already. Once more, we have water pressure, earth pressure, and we have the conditioned ground. And through the screw conveyor, I'll take out the amount of ground necessary to come forward. This is also one very important thing with these EPB shields. With a mass check, you can immediately see how much ground loss you're producing. And you can also monitor whether you take out too much ground, because that there is a risk when you go along that you overcut, so that material is falling in and creating a void on top of the machine. And that can be only seen when the mass balance is always kept. So now, short comparison, slurry or EPB. I mean, one thing is very clear. Slurry shields need a separation and treatment plant. EPBs do not need that. Then with the EPB, you're a bit more flexible with the mucking. With slurry shields, you have to muck through the pipes and they must be there. And depending on the ground condition, it can be that these pipes are also subject to wear and tear. There was a project not in India, outside India, where they had to basically do repair welding on the pipes because they were not there anymore. The material was so abrasive, and whenever you had a 90-degree bend, there was friction, and that took away the steel from the pipe. And well, most probably because it is relatively simple to operate and also not much space consuming, EPB is the prevailing system that is used in India. So when you look into Delhi Metro, was all EPBs. Mumbai Metro was EPBs and some other machines which had EPB mode and some other open mode. And I think only one lot used slurry shields. So one can say EPB is the more popular one, also coming from the constraints of the space. In Bangalore, currently, some slurry shields are working because definitely for the ground condition, they are more appropriate in terms of wear and tear. And one big thing is, or big advantage of the earth pressure balance shield is that you can go even with the normal EPB in open mode, then you are a bit faster. And that was done in Mumbai in several stretches where there was no water at the face. Then going in open mode was a very viable option. So, and one thing to the cutter heads, I think here it's becoming again very obvious. The left one is for soil only. So with that, you can go through sandy silt, sand, whatever is there in many metro areas, especially when you're close to the river. And this shield here is from Metro Mumbai. And you can see that is having all the traits of a hard rock cutter also with discs, because a good amount of the stretch where the shield went through was hard rock. But still, this can be also operated in softer ground. These shields, it's always then a matter of design and a discussion with the shield supplier, what is the best cutter head. And also you can see the opening ratio, that means the area where material can come in. On this rock cutter head, it's relatively low. And here on this EPB shield, it is very high. So whatever is mixed in here will immediately take the pressure from the face. So, and just to give a brief idea what such a cutter head has to endure, left-hand side is at the start when the machine was lowered, and on the right-hand side is how the cutter head came out after driving. So all these nice paintings have been already, been gone. It looks relatively well. there is no obvious damage, but wear and tear was there on that cutter head. Now, proceeding towards the metro, one thing that is something quite peculiar nowadays is that we can say that we have a standard metro ring. All the metros in India having, not all, but most have the 5,800 millimeter inner dia. Most of the precast lining segments have the requirement to be 275 millimeter thick. And then the list of metros where these rings are used is already quite long. Only minor deviations were there depending on the metro system. But this is how it looks like. It's a more or less a standard SOD. So when it comes to this part, not much design study is required because these dimensions are already given. Only when they should change, when requirements change, there might be a rework of that geometry. And usually segmental linings nowadays in metros are so-called universal rings. So basically I have a taper on the ring, which allows me to negotiate curves in horizontal and in vertical. So basically the machines have
वो फिर बार बार फोन
उठाएगी नहीं, फोन उठाएगी तो तब जब उठाएगी होगी इसी तरह।
Okay. So the machines or the segments have different positions. Usually the machine supplier has a software which goes through the ring positions and calculates before the driving already the best position for each and every segment, because that is then a task in itself to have the right order of segment positions so that you can maintain your horizontal alignment and your vertical alignment. Because you're not just going straight, you may have a curve. And then the machines also have functions that you can update that. Because if there is a small driving deviation, you have to recalculate the full ring sequence ahead so that you can compensate for anything. But these universal rings are now used everywhere because they are the system that is working best and is most flexible. And one thing is also there, once the molds, and that is then, so to say, going back to the standard metro ring, once the molds are ordered, molds can be reused for many projects. So only if the specifications change drastically, then they have to be replaced. But usually a good set of molds can be used for 3 projects. And that means if I have, so to say, a standard taper in my molds, which is applicable for the next project, if the taper is too small, then I cannot use it maybe because the curves are tighter. And the thickness is fine, then one investment in molds is working for many projects. Now coming to the overall planning. So it's not in metro tunnels that we have 2 portals and then we meet each other somewhere, because there is stations, and not only stations, in many places we have different ground or changing ground conditions. Let's put it like this. If you take Delhi, in Delhi you can have soft soil, this silty sand of Delhi, and you can have hard rock. Mumbai also, the soil profile was changing. This is an example from Mumbai. So that's the first step, so to say, where the soil profile and the water levels are being drafted, being also shared with the contractors in the tender stage. The stations are being marked, and then contractors will start thinking, I mean, this is nothing to do with the geotechnical design, this is then more logistics. How will I drive? And that is already an interface or a coordination work between the TBM contractor, the designer, especially for the launching and the retrieval, then the station designer, because he has to prepare each and every station for retrieval or launching. Whatever space requirements are there have to be considered. So logistics play a heavy role in that whole driving sequence. And then comes also the decision whether you drive through or whether you basically retrieve a TBM and relaunch it. That makes a huge difference for the contractor. Maybe not for the designer of the TBM segmental lining, but for the contractor, it has a huge impact. So, and launching, and here's retrieval, that is then done by separate shafts if it cannot be done as part of the station. This example shows Mumbai package 4, where, so to say, in City Vinayak was one launching focus, and in St. Xavier was another launching focus. And then, so to say, the point where the designers are coming in again. I mean, this L section is already stemming from a GAR, where all the drillings, the exploratory drillings, ground investigations are being, so to say, collected, summarized, and put into a drawing. And not only this, in this drawing here, there is a bit more inside, and I'm coming to that later. There is already recommended phase pressures, maximum phase pressures, tail void grouting, and air pressure for cutter head intervention shown. This is parameters which are coming from the design, as sort of recommended parameters, to give a range of values for a safe driving and safe intervention in the machine. Because if you cannot, or if you don't keep that air pressure, the problem may be that you have water inflow, and depending on your ground, that water inflow may drag along also material. And in worst case, you can, instead of only maintaining your machine, you build a sinkhole slowly. Now, I think that was good enough for the introduction, and slowly coming to the metro tunneling. Now coming to the design tasks for the metro. I mean, we have two main things where the designer is putting his efforts in. I mean, one thing is the lining design, which is usually the more obvious, what everyone sees. But then we have also what I call the driving design, and that would be phase pressures, grouting pressures, intervention air pressures, as already mentioned. Now, lining design, there is already a number of recommendations, and I can only recommend to go through them. ITA has published guidelines for the design of segmental tunnel lining. The Germans, which is also an ITA sub-organization, have produced recommendations for design, productions, and installation. And there is a code of practice from the UK which is also dealing with the design of concrete segmental linings. So this topic is covered, and there is a number of sub reports which are there for precast linings with fibers, backfill grouting, etc., etc. So I would really recommend go to the ITA website because there is a real big collection of up-to-date papers. Now, from the ITA guideline, lining design, what is to be considered? So it's not that we only look at the lining design like we would do in a cast in situ lining, where we look at the final product mainly, but here we have production and transient stages, which have to be considered in the design. Because it starts when we demold the segment, there will be forces on the segment during the storage, during transportation, during handling. And then this all is covered by some load factors, which ITA is proposing. Then comes, so to say, after production, the construction stage. Now all our machines are pushing against the lining. So the thrust check forces are one of the decisive loading for our tunnel lining. Then comes tailskin back grouting pressures, secondary grouting pressures, and in some cases, the TBM backup load, because behind the shield there is another 100 meters backup with many equipments. And then under point 6, finally, we come to what we would usually see in the geotechnical design as our lining design. That is then the ground pressures, groundwater surcharges. Then in the radial joints or longitudinal joints, the bursting loads that is to be looked into so that they are not damaged. Loads induced due to additional distortions, that is to be seen always, depends on the driving, and other loads. So compared to a normal design of a cast in situ lining, we have two big areas which are, so to say, extra. Now coming to that, we have the demolding done here with a vacuum lifter. Again, these forces have to be checked on green concrete. That's the thing where the concrete has no strength whatsoever, or very little, let's put it like this. Then comes the stacking. How much distance is there between the blocks so that there is no issue with the segment? Transportation, yes, and handling is basically to look also into these inserts which are there. Now, coming to the thrust check forces, I mean, it's very, actually very simple what these forces are. I'm having groups of checks which are basically pushing my machine forward, and they are pushing against the rings. So I have relatively high forces introduced locally, and the segments should not break when under load. That means that I do have a development of stresses which I have to get under control. And as written in the guideline, there is simplified approaches, there is diagrams, and even finite element analysis to get an idea how these checking forces will load the segment and where do I have stresses which are, so to say, disadvantageous for my concrete, because I'm still using concrete for my segments. Concrete has a very good compressive strength. So in compression, there is usually no issue with these checking forces. But then, so to say, together with the compression forces, tensile forces will develop. And that is the so-called tensile loading that has to be countered. Concrete itself, especially higher quality concrete, has a tensile strength. So in many cases, this is sufficient. And then localized, the bursting forces also have to be seen. But again, with the high concrete qualities nowadays, it is better under control than earlier. Earlier, bursting meant to have a lot of bursting reinforcement inside, over and above the normal main reinforcement. Now the tail skin grouting pressure is shown here as a diagram, and usually it is not a very decisive load case because it is quite uniform, and in many cases already this load case is already covered with the normal ground load. So good to check, but in this specific case, it will not give you, will not have much impact. Let's put it like this: there is more decisive load cases, but this one is more important as a load case, and that is basically after some time, the secondary grouting will happen. And secondary grouting is really to have the last voids closed. And secondary grouting also has the, or is done with the objective to balance out anything that might not have worked nicely during the driving. Here it's shown that there is in the crown some, so to say, gap. And when you look at this, it becomes very clear that this also helps to mitigate settlements. Because if I'm having some voids and cavities above my tunnel, over time it will be filled with material, and that material can only come from above. So, and that means it will settle downwards. A proper backfill grouting can do some mitigation on the settlements also. And the secondary grouting is usually done through the rings. There is a grout plug, which is at the same time a lift for lifting socket for installation, and which has also a no return valve, and through that grout is being applied to fill whatever voids are there around the segment. And each segment has one grout plug, so one can not only take one position, one can in total have 6 positions where you can grout. And for the structural engineer, or for the one who is doing the structural check, it means that he has to check with such a loading that we have, so to say, a triangular load which has a certain maximum grout pressure. And that basically shows now what is the interconnection of different design steps, because when the usually within the phase pressure calculations or in this whole package, there is also the maximum grout pressures, and they have basically 2 values. One value is how much phase pressure do I have. I cannot go with my grout pressure higher than the phase pressure, too high, because otherwise I may have grout coming into my face. And on the other hand, I have a certain limit for what the segment is designed. in terms of ground pressure. I cannot go beyond that, except I take the risk that the segment may be damaged, or I'm having so good monitoring for this specific case that I can say, okay, I go beyond that and I monitor the behavior of the ring so that I know very quickly where I have to stop. Now coming to the permanent loads, which are there, like groundwater pressure, any surcharges, which is again something very specific for urban tunneling, that I have to assume that buildings are above my tunnel or buildings might be built on top of my tunnel, and they are acting on the full ring, on the single segment, and on the joints and gaskets. So all these have to be checked. So now coming to the ground loads, there is some difference compared to what would be called the normal mountain tunneling outside the cities, because in many metro contracts, the ground load is to be taken fully. So that means there is no relaxation permissible. What we do in rock tunneling, that we say, okay, we let the material relax even in our design calculations, is not admissible in many of the major employers' requirements. Then, when we take this whole thing one step further, the overburden and the coefficient of side pressure, the K node, determine our stress level, and also the uniformity in the sense that I'm having horizontal stresses and vertical stresses. And at the end, I'm having a segment ring which has to balance out these two stresses. And one thing that I think cannot be overemphasized is that the subgrade reaction modulus, so to say, a value that is governed by the ground, by the stiffness modulus of the ground, the radius of the tunnel, and in some approaches also the Poisson's ratio of the ground, is another very, very important factor, because it basically describes what resistance segments would meet when they try to push into the ground. So we have to see two things. From the top, usually the load will come and the segments will start, in the ideal case, to overlies. And that means that part of the segment will push into the ground. And that pushing into the ground is met by a reaction, which has to be seen very carefully, because that can determine a lot of things, or has an impact, especially on the bending. So, and usually the sectional forces are determined from the ground load and the groundwater pressure in one go. They can also be calculated separately if because they can be separated out, but the usual approach is to have them both in one go. Now, the accepted procedures which are being used for these calculations is in all cases an analytical approach, the so-called Muir-Wood equations. It's a paper from 1975 with a discussion contribution also from another engineer, Mr. Curtis. And in the German-speaking countries also there is a publication or several publications from Mr. Dudek and Mr. Erdmann. These two gentlemen also had developed an analytical approach to determine the sectional forces in the lining. So the bending moment and the normal force. Then the other accepted procedure is to make a beam spring model with any structural software, whatever is available. And one of the standards nowadays is that we have a numerical calculation either with finite elements or with finite differences to see what is the load and the sectional forces coming from that loading onto the ring. I have to say this is all on the level of the ring. There is no requirement to model each and every segment separately. And it would also not make too much sense because we have quite a good number of positions. So one has to run several analyses with no additional gain. So now coming to finite element analysis, this is the model for the twin tunnel before anything happened. Already the surcharge is shown, which is 50 kPa, which is a standard value in many metro requirements. And then we have, so to say, also shown here nicely the different ground conditions which are there with the material parameters, unit weight, etc. And that, so to say, would be the starting point for the calculations. And at the end of the day, as you might have seen already, this is the result. In this case here, it's about the bending moment in two adjacent tunnels. This is something which can be done with the finite elements much better than with any analytical solution, because I can assess what happens in the first drive. Say that right-hand tunnel was the first drive. The first drive tunnel will get a bit more loading than the second drive because whatever changes between first and second drive must be endured by the lining of the first drive. So, and that brings me to this very short comparison. We have on the one side the Muir-Wood as an example for an analytical solution. It's simple to use. It's an elastic solution. What is, I think, the highest plus point for Muir-Wood and all these solutions is that they can be integrated into an Excel sheet or into any, so to say, tables for repetitive analysis along an alignment. Because I can run several calculations. I can even play around with the load cases, with the water level, and it's not as sophisticated and complicated as a finite element calculation. So for parametric studies, this is definitely a very good solution. Shortcoming is definitely that the mutual influence of two drives is quite difficult to analyze. And one thing is that in many cases, the results are higher in terms of the sectional forces than coming from any finite element or numerical model. But still, these approaches are part of any design. And then come the finite element calculations, very simple, mean I need more time for a proper modeling. There are definitely more parameters to be considered, which can be very interesting because also nonlinear soil models can be taken into account. I mean, soil is a highly nonlinear material. So a nonlinear model like a strain hardening model will make a lot of sense if I have the basic parameters to operate it usefully. Because otherwise I might be having a calculation which looks very precise, but is completely wrong because my basic parameters are not correct. But there is many benefits. And what is definitely the big plus point is that the tunneling influences on the sequence of tunneling, complex situations like tunneling close to a station, after the D-walls have been done, before the D-walls have been done. All these situations can be simulated with numerical modeling. And that's why, especially when I have a heavy built up area where I need to take into account certain things, I'm better off when I do also one analysis of that complexity. So then coming to other loads which are to be considered in the segmental lining for the metro. I mean, fire incidents, that has to be considered, but usually simplified methods, because I don't have good trains in my metro network. I don't have carbohydrates in my network. So my fire loads are comparatively low. And a simplified method, like given in the Eurocode 2, is deemed sufficient for that analysis, because usually I just want to see, is my cover good enough? I'm having a reinforcement. Will this segment withstand so that I have no problem in terms of stability? Then the other point is definitely, well, sometimes under discussion, but seismic design is also there. And for that, again, the finite element codes do have some algorithms for seismic design. Usually it's not the governing load case for tunnels, also not for TBM tunnels, but it will be considered and should be considered to have everything in place and everything checked. Because it could be that we have local overloading, but no major instabilities. So, and once all these loads are being analyzed, being assessed, it's all put together in different load combinations, and they are then checked as per whichever codal framework is chosen. I mean, Eurocode is acceptable in many places, and the Indian standard for concrete can also be used for most of the cases to satisfy then overall the reinforced concrete design criteria. So these things have to be taken into account, because that's actually the thing that is important, because the next step is then durability considerations. I mean, metro tunnels are exposed to sometimes harsh environmental conditions, not in terms of temperatures, but in terms of chemistry. I mean, just imagine Pune and Mumbai, where you have salt water around, where you even have a little bit of salt in the air. So that has to be considered. The design life is 100 years. You cannot just repair somewhere below buildings, will not work. So concrete degradation and the corrosion of the reinforcement have to be mitigated. That has to be looked into. And the durability of the structures has to be ensured. And there is several measures. One thing is definitely inspection, preventive maintenance, and repair, which is something standard. Then the next point is material choice and quality control during production. That to some part touches the design, and then comes things which are, so to say, directly in the realm of the designer, that is design parameters like the concrete cover, concrete mix designs, recommendations in this regard. And so there is codes which prescribe minimum covers. That is the in the European code, the EN 206. And the British standard has the so-called BS 8500, which is, so to say, complementary to the Eurocode. And there, basically, one is walking through a procedure where first the exposures are being defined. So am I in a saltwater environment? Am I in a marine environment? Am I in a normal environment? And from there, the whole process starts and one gets into the different exposure classes. And each exposure class then, together with the concrete strength class, will give minimum nominal cover, which has to be taken into account. Also cement qualities and cement types are being defined on that. This is quite a comprehensive document. And with that, going through that, already certain decisions can be taken. Then comes, there is a water penetration test, which was earlier always a DIN code. Then there must be, there can be in the specifications values prescribed for the rapid chloride penetration test, which is basically a test to see how deep can chlorides penetrate into the concrete. And usually that RCPT value is linked to use of certain admixtures and components in the concrete, like silica fumes, to ramp up the resistance against chloride penetration. These are also usually given in the employer's requirements. And then, so to say, when all this is done as per the codal provision, it may happen that clients ask for a durability analysis, and there is a software tool. The name is mentioned here. It's Live 365. It's free of cost. You can download it from the internet, and it basically allows you to analyze when you have a concrete cover and the thickness of a wall to see at what time will the chlorides penetrate so much that they induce corrosion. And based on that, the design life can be estimated. I mean, the whole background is coming from the International Concrete Federation, FIB, but this is, so to say, the tool which can be used by the designer. And you can see that here it's just the base case was normal concrete, and in the alternative, the water cement ratio was reduced. There was slag added, silica fume added, and then the design life went up. I mean, this is here numerical values 150 years plus, but it basically means that from the probabilistics, there will not be corrosion in that depth at a certain point of time. Now we have checked, so to say, the ring. Now we have to go one step down. The bolts have to be checked, or whatever is there in terms of connectors on tension and shear. The erector socket has to be checked whether it's stable. The gasket pressures have to be checked in two ways, in terms of geometry and in terms of load induced through the compressed gaskets. So this is something which makes, or which highlights how complex at the end of the day a precast lining is, because I'm having molds which are unchangeable. Once they are defined, they are like this. The molds define the geometries of the joints where the gaskets will be put in. Now, this cannot be changed. What can be changed is the gasket material. And there is gasket suppliers who have relatively stiff gaskets and gasket suppliers which have softer gaskets. And it makes a huge difference because a softer gasket will not develop that strong resistance against compression. That means the load for the design is also less. And when you think of the two rings being pushed together, I'm having the gaskets there, it makes a difference if the gasket develops, say, 20% less strength, because at the point after the the ring has been erected, the bolts are fixed. If my bolts on tension cannot take the loads which are coming from the gaskets, because eventually the chain will be retracted and the load will go on the bolts, then I may have a little bit of problem here because of the gaskets. And the other thing would be in the, so to say, in the radial joints, that the compressed gaskets exert too much force, shear force onto my segment, and it may break. So this is something which at least has to be checked, that it fits into the whole system. And then one quite important structural check is to check the joints, the radial joints and the circular joints. So circular are the ones which are basically subject to shoving loads. Then their governing load cases are usually over. But the radial joints, or sometimes called longitudinal joints, they have now loads coming from the groundwater, because all the hoop forces which are there in the segment are transferred or not through this joint. Now, coming to the joint stresses, this would be stresses for a flat joint, completely flat. You can see this would be for the gasket, it's the inner side, and how the contact is going. There is a normal force, there is an eccentricity. Either the joint is fully compressed, that is good. This is not so good when the joint is not fully compressed, because how will then the loads be transferred? Only with very low loads this will work. So this is taken from this ITA guideline, this sketch, but this is something very important because it is also depending on how the geometry of the segment is at the time of the loading. Because if I have bird's mouthing, this here is called bird's mouthing, that the joints are opening like a bird's mouth, I do get concentrated loads in one place, and then I might have trouble, so to say, transferring the loads from one segment to the other. Now, one thing that is done very often in metro tunneling is then that we take a convex joint. You see, you can see it only very slightly. The two ends, also in the molds, are convex. So if there is a slight rotation around that point here, where the bolt is sitting, there is not, there will be no moment introduced. It will be still a contact force. So the design then has to go for a concentrated force transfer, but it's not that I'm getting here, like in a flat joint, bending moments inside. So this is one thing which is very common in this metro tunneling, that we have convex joints, which allow a little bit of flexibility and take advantage of the concrete compressive strength. And you can see here what I said earlier, this gasket groove, which is there. Now that is also compressed. And you can imagine when there is a load coming here and coming here, that it may break out here. Just sketch it in. So the loads would then be this direction, but the breaking out could happen somehow like this or like this. And that is not good at all. That's why this here has to be checked when the design is done. It's a detail check, but it has to be done. Now, the last big topic for urban tunneling, I would say, because we are talking about low cover and keeping all things stable all the time, is phase stability. So this is how one can imagine the loads acting onto the cutter wheel, onto the tunnel machine. So at the end of the day, I do have a sort of sliding wedge, which is held here in place. So, and that sliding wedge can go in both directions. It can come down like with active earth pressure, and it may also go up, which is also highly undesirable because it would mean heave. And on the right hand side, you can see a failure mechanism, which is already, I mean, this is a planar or a 2D picture, and this is a 3D picture. We have our tunnel here with the face, and the assumption is that there is a wedge, and onto this wedge we have ground and groundwater as a load, and this is trying to push in. So, and more complex studies have been done for failure mechanisms, which are variable because in the first one we have cohesion, and in the last one very little cohesion. Middle one, no cohesion at all. This would be like in the sand, where the failure mechanism looks like this, and in the clay material it can look like this. So this is then studies which have come up later, but at the end of the day, wherever this red circle, which represents the face, is there, we have to apply enough counter pressure to not let the ground collapse or become unstable. This is, for example, not an issue for any rock TBM, so in soil. And at the end of the day, I'm coming up with a range of phase pressures. And the thing is, the lower limit pressure is basically coming from an active earth pressure coefficient. Then I'm having my operational range with certain deviations, which I have to get into control, but which are there. So, and the upper limit of pressure is basically to avoid any breakup and blowout. And if I'm going further up with the pressure, which is feasible because I can push my shield in and don't let any material come out from the screw conveyor, for example, then I can have even a passive failure and heave on top of the tunnel. So this here you will not get really with a slurry shield because you have earlier blowout. But with an EPB and you don't let any material out, you can end up with such a situation. However, from design end, this is what we need, what we want, that we have, so to say, the phase pressure in the operating range. Here it's given as at the tunnel crown. Usually there is three sensors, at least three sensors, one in the crown, one in the sidewall, one in the invert, to see how the phase pressures are developing during driving. So, and this would be one diagram how to calculate all these forces on the face wedge. It's taken from a TAUB guideline, which is a guideline only for the determination of face pressures. So you can see what all is being taken into account. We have the vertical load from the ground, we have the water pressure. There is, and that is shown by these arched arrows, a sort of arching or silo effect, which can be taken into account if you do the determination of the vertical stresses with the Terzaghi formula. Then you have a sort of a silo effect already inside. And then the different values coming and from ground parameters like friction, like cohesion, which all in all together will give, so to say, a balance of forces which has to be kept. Now, one thing that is coming and which is not shown here, some formulas, also the formulas of Anagnosto and Kovari, they are taking into account some seepage forces, because at the end of the day you can be completely watertight, but you can have a little bit of seepage, and seepage means also seepage forces, which on the other hand will reduce the water pressure at the face, but you will still have the vertical pressure. So this has to be taken into account, and also what is allowable in that. So these are the recommendations for support pressure calculations, and then the two main papers which are generally accepted. There is even more in that guideline, which is very comparatively new. Let's put it like this. You can find other approaches also, but Anagnosto and Kovari are in this respect a reference for the face pressure calculation. So then one last word on this here. This is settlement control, which is paramount in urban environments. So the face pressures and also the ground loss, what we calculate, are the influencing factors for the settlements. Because earlier I'm taking a ground loss into consideration for my settlement calculation, but then I have to see that I can maintain this ground loss, what I assumed. So then the face pressures come into the picture and other measures. And one of the measures is the second stage grouting, the backfill grouting, which is a very important mitigation measure. If something happened, I can at least grout a bit to counter that loosening. So that can reduce settlement. And usually in a calculation sheet, that must be considered, that what would be my backfill grouting pressure if I want to keep the whole thing, say, elastic. For information and for further determination whether it's feasible, workable, and what will happen if I cannot maintain it, how much will I get finally. The reference I've given here, it's an ITATEC guideline for best practices in segment backfilling, to see what is there, because that is very crucial. And now if we think only in cross sections, we may overlook the importance of the segment backfilling. But not only settlement control, also when we go back to the whole segment design and the checking design checks consider that I have a segment that is more or less fixed. If the segments are not backfilled properly or something happened, the whole loading scenario will change in a manner which is very difficult to grab in a design, and also in a manner which, when you take these loads as inputs, will be difficult to really make an economical design then. So that's why the whole system must work together very well. So thanks a lot for your attention. This should be the end of a successful drive always in metro tunneling. I think I will hand over to you. If there is any queries, questions, most welcome. Just trying to get the chat open. Okay.
Yeah,
Good.
I have some questions. So one
Okay.
is in the chat box. I'll just read it out loud. How are the dynamic loads of metro trains on segments factored, and how are cross passage junction model? Please, like just a brief.
Well, there is one thing. The dynamic loads. What load of the trains is there, but it's usually so small compared to the other loads that it's not considered. We sometimes consider the first stage concrete, yes. What was the other? Cross passage junctions. How are they modeled?
Yeah.
Well, I mean, there is one thing that is usually done, that you model them in Start Pro or any software. You could model them in 3D finite elements, but it will not help very much. Usually we take the forces from the rings and put them onto the steel frame, which is integrated into that opening. So in metro tunneling, you basically have first the rings to support adjacent segments. You open one segment ring, maybe you open 1.5 ring, means you cut a little bit in the other segments, and then you put in a steel support ring as a final support, which transfers the loads, and that's how the whole thing is modeled.
So yeah, the next question is from Mr. Tushar. So he
I
said,
think there was one question was about drive-through procedure, or is that already clarified?
Yeah, we have from Mr. Siddharth, brief about the TBM drive through procedure adopted for passing through UG stations.
Usually, what we call the drive-through is that the D-walls are already there, and the machines are, so to say, driving through, but the excavation is not yet done. That would be a drive-through situation. I mean, we had one situation in Ahmedabad, which was also, you can say, drive-through, but at that time the D-walls were not even done because the land was not handed over. That was again something different, because then we had the normal driving, but had later on to verify through design what measures are to be taken that the tunnel will remain stable. I mean, it was nothing really big at that time. So this is for the really drive-through procedure. Usually you would have already your D-walls ready, your station box, but you have not excavated the same. And then you drive through. So from the segment point of view, it's not a big deal, because the segments will be taken out later on and usually even broken. So if we know it, we can put in sacrificial segments with lesser, so to say, specs. And regarding this SOD, that is a very good question. In India, there was a time when every client had a different walkway width. Now it's being standardized slowly. So if the client gives the SOD, then this is to be followed. So you may find different drawings on different metros because it's also an evolution. What is happening? And this.
And we have the question about phase pressure calculation, also done by Proctor and White method. So I think it's just a reference, I guess. And any recommended pressure range for backfill grouting in EPB, TBM tunneling?
See, this is, I mean, usually the design foresees that you have 500 kPa maximum pressure because that's the design case for the segments. That's 5 bar for the backfill grouting. And the lower value is coming from other boundary conditions, but the pressure range is to be calculated. There is no recommendation. There is a calculation. Like what we do as engineers, that we calculate the things and then put them into a sort of breakup.
Okay.
Okay, I see the next one. But the slurry machine can go with hard strata. The slurry machine, it's the cutter head. But it would be then, if I expect some hard strata or some rock, then I would have a cutter head for rock, and then we will not get stuck. I mean, the thing is, I think my screen is still visible. I will just try to go back to this thing with the cutter heads. Yeah, if I have such a cutter head, I can go through hard strata. And the main issue is usually not the strata. It's an issue, but the point is, if I have a uniform hard strata, I'm well off. If I have a uniform soft strata, I also have no problem. If I have mixed strata, then I have a problem, because then half of the cutter head, say, maybe even diagonally down, is hard rock, and this part is soft soil, and that is a special case which can be very, very tricky to solve, because I need enough pressure to keep that in place, the soft soil. And on the other hand, my main counter forces are coming from the hard material, from the rock. But still, it has been done. And the slurry machine is actually a good machine for hard rock. So if the cutter head is prepared for that, then we will not get stuck. We will get stuck when we have a soil cutter head and heat rock.
Okay, so any more questions from the participants? So I guess we don't have many questions for now. So thank you, Dr. Crane, for your wonderful webinar on this brief overview on TBM tunneling. I'm confident your experience will be very helpful to everyone. And to the participants, I would like to inform that all our past webinars are also available on YouTube channel, and this webinar will be uploaded shortly. And once again, thank you, Dr. Crane, for sharing your experience, and thank you for joining.
Well,
have a great weekend.
Most welcome. Thanks. Same to you. Have a very great day. And yeah, let's hope that we meet again in person.
Yes, yes.
All participants, and we can exchange certain details which can't be covered in such a webinar in a short time.
Sure, sir, sure. Thank you.
Okay. Thank you so much. Thank you.
Thank you. Bye.
Thank you. Bye-bye.